Hello, welcome to the 12th Orbiter tutorials. This is going to be a two-parter episode. In previous episodes, the way we've done things is we would plan as we fly. But the minute you start talking about going to another planetary body, you can't plan as you fly because there's too much to do on the fly, and you can end up screwing yourself over by not planning ahead. So part one is going to be, and there it goes again. Part one is going to be actually planning the mission, and then part two is going to be execution of the mission. So part one, we are going to outline the 8 phases for a lunar tutorial, and then we're going to extrapolate those phases to build the mission outline, and then once we have the mission outline, we will label the critical phases of flight, which are time critical and exists the possibility of mission loss. Alright, so we're actually going to have 5 deliverables. I forgot as well, we're going to want to have a table of mathematical equations, and I'm actually going to build them on screen so that you can follow what I'm doing this time, instead of me just displaying stuff up on the screen. When you're done finding these things, you want to stash it somewhere so that you can reference to it throughout your mission. I also advise not breaking the calculators, because every once in a while, if you make a mistake, you might be able to make a calculation on the fly and save yourself, instead of having to declare the mission as a loss, which is extremely important. So we're going to get 5 deliverables out of this, and here we go. So we're going to build the mission phases now, and this is going to be a lunar tutorial. And there's going to be 8 of them. So let's go ahead and outline the 8 different phases once my Excel skills actually catch up to where they should be. Okay, so the first thing that you need to do is you need to sync up the lunar plane, the lunar orbit plane around the Earth. So the moon orbits the Earth, and it's just like the International Space Station. It has its own orbit plane, at which if you launch into it, it'll give you 0 degrees of inclination. That way you don't have to do a costly plane change, and you can actually just straight up fly to the moon for a low cost. This is exactly what Apollo did. The second thing is going to be actually not launch and ascent to orbit. So you get into a parking orbit, and there you're going to check out all your systems and prepare everything that you need in order to run everything. Now the real exciting thing is the TLI, the Trans-Lunar Injection. So that is something we haven't done before. That is where you burn the orbit in a prograde direction to raise the apoapsis, or highest point of the orbit, up to approximately 384,000 kilometers above the surface of the Earth, where we will intercept the moon, and we will intercept the orbital path of the moon when the moon is actually going to cross it, which is one of the most important things to do. The next thing is going to be a lunar approach. Again, this is something that we haven't practiced yet. This is targeting a specific entry orbit and in a specific inclination that you're going to use to travel around the Earth. The moon. So the issue is, with the Earth, you have a shift westwards of 15 degrees per hour because the moon rotates, here we go again. The Earth rotates underneath your orbit. The moon has a sidereal rotation period of approximately 28 days. That means a progression of a That means a progression of the orbit westward at half a degree per hour, perhaps slightly even longer because an orbital period around the moon is even longer. So at half a degree per hour, you would be waiting up to 360 hours to have anything done, which is multiple weeks to be able to, it's about 2 weeks to be able to access the entire part of the moon. So getting your inclination right is critical when you approach the moon, because you can't wait for your base to move under. The next thing is going to be your base transfer orbit. And this is going to be, yes, I skipped. Sorry. That's actually going to be the 6th step. The 5th step is going to be the lunar orbit injection. And this is fun because this is where we come flying past the moon. We're going to be in a strange type of orbit, which I have not discussed yet, called a hyperbolic. Well, that's not necessarily true. In the last tutorial that went over the different elements, we're going to be coming in with an inclination, not an inclination, an eccentricity greater than 1. So we're going to be coming in with a hyperbolic path, and if we don't do something, we're going to go flying off into space. And that's an exact example of a critical mission phase, where we could encounter mission loss. So I'm just going to mention that, and we'll detail on it a little bit later. So what you do is you go from just flying past the moon at a high speed, you kill off all your speed, bring your orbit in. Now you're orbiting the moon in a circle. Low lunar orbit. It's something that hasn't been done since 1972, I believe. And, well, at least with man. You're going to be orbiting just about 100 kilometers or so above the surface. There is no need for a minimum altitude other than to avoid striking the surface because there's no air. So you can actually orbit the moon to the level where you actually impact the surface. There's no real restriction on how low you can orbit until you actually strike the solid surface of the moon. So you can theoretically orbit at 2 kilometers altitude, but more than likely you're going to hit a lunar highland that's above 2 kilometers. The moon, I believe, has about 12 kilometers of relief, so you really don't want to get any more than 24 kilometers below the altitude, to account for the worst case scenario, lowest point to highest point. Let's see. Base transfer orbit. The base transfer orbit is going to be where we lower our orbit from that safe kind of 100 kilometers all the way down to the 24 kilometers, the lowest you can possibly get to the moon without actually striking the surface along the way. You're going to get really close to the moon, and then you're going to begin slowing down. So that's a deorbit. Deorbits is something that we haven't covered yet because it's not the re-entry. On Earth, you have an atmosphere which will slow you down as you begin to re-enter. In the case of the moon, if you don't slow down via running your engines in a retrograde direction, you will impact the surface. You will not slow down in any way, shape, or form. So what you have to do is you have to do a retrograde burn, and you have to continue burning until you're stopped above the surface. And this is where my last tutorial on your velocity vector is really important, is because if you don't do this in the right time or in the right direction, you're not going to be above the base, and you're going to be wasting that precious, precious fuel. The last, and perhaps most important, is the landing. This is where we perform a hover descent, a vertical landing onto the surface, preferably a pad of your choice. And this is probably the most critical phase of flight, because if you don't start accounting for it during your deorbit phase, you're going to accumulate so much vertical velocity in falling that you'll be unable to save yourself before you crash into the surface, and that will end your mission. So those are the mission phases. So the next thing we're going to do is build the mission outline. Okay, so now I've placed our mission phases into the mission outline. So we're going to drill down to the next step, or the next few steps on this level. So the first thing that we're going to do is bring up the map MFD, and you're going to target the moon. And what you're going to do is you're going to wait for, well, first calculate and then wait for the takeoff time. And then we're going to calculate our azimuth, obviously before launch. Okay, so then we launch. So the first thing that we have is orbit injection. So this is actually getting up to orbit. It's possible, based on the geometry or how good we fly our launch azimuth, that we might have to do a small plane change. So we're going to account for that. And then we go into planning the TLI. And we're going to use a special MFD for that. And then from that, we need to record the delta V that the tool gives us. And then we need to calculate the burn time. Okay, now we're on to a translunar injection. So then you have a TLI burn, nice and simple, and this is calculated from that number. So that's how we get that. And then what we're going to do, potentially, remember I talked about the oscillating elements and how there was a potential issue with things changing. And you remember, as we approached the ISS, when we started to get close, we would need to do a little bit of a correction adjustment. So we might have to account for a small mid-course correction maneuver that will adjust our path to ensure that we do in fact meet the moon. Our lunar approach will involve a base target burn. And we're not actually going to calculate that. That's going to be a kind of touchy-feely thing, because you would need numerical analysis to solve it, and I really don't feel like doing that. I feel like it's beyond the scope of this kind of tutorial. When we do the really crazy stuff like multi-planetary hopping, I might do that, but for now we're going to leave it there. And so then when we get to lunar orbit injection, so then we're going to use the vis-vifa, which I introduced last time, equation to calculate orbit entry delta V. It's extremely important. And then perform orbit entry retrograde burn. Then we're onto the base transfer orbit, which means we need to, step one, identify the base's longitude. And implied that the burn is going to happen at the longitude minus 180 degrees. So this is just going to tell you exactly when to begin your deorbit burn. It's different than it is from the Earth, because the atmosphere will arrest your re-entry burn before you actually strike the surface. So that's why, you know, it'll show that we're actually impacting somewhere around, we'd impact somewhere in the Atlantic Ocean, but the atmosphere actually will bring us down to land in Florida first. So that's an example. In the case of the moon, it's exactly 180 degrees off, because there's no atmosphere. So you want to be down as close to the surface as you can get in that time. Okay, so next is going to be the base transfer burn. actually perform the base transfer burn. And it'll be quick enough that we won't have to do a burn time solution. If you're off by half a degree of longitude, you really won't notice it. The burn should not take more than about 30 seconds to do. So then you're going to deorbit. So now what you're going to do is you're going to need to do another vis viva equation calculation of the distance that you'll need to slow down. Well, actually, first, velocity to kill. So you're going to find the amount of speed that you need to kill. And then, you know what, I'm going to add another line here. And then you're going to use the acceleration to distance formula, which I'll go over again, to calculate distance to stop. And that's where you're going to start slowing down above the base. And then once you're in that configuration where you've now stopped, you're going to calculate total potential energy, which is known as U. And then we're going to solve for velocity gained in K, our kinetic energy. And that's pretty important because that's going to tell us exactly how fast we're going to reach when we get to the ground. That'll tell you roughly when you should begin slowing down. Now I'm actually going to insert another line here, and what we're going to do now is tune the VOR of the base. And that's going to tell you where your relative velocity vector is compared with the base itself, to make sure that when you stop, you're actually stopped above the base. Okay, so now you're going to calculate hovering distance to hover at gained velocity from the potential energy and we're not going to factor in our changing fuel rate, but we will factor in the lunar gravity. If you don't factor in the lunar gravity, you will screw yourself, because the hover engines have a capability of about 7 meters per second squared or something like that. We'll get the actual numbers when we perform the calculations. And the actual craft, or the actual gravity of the moon is going to be about 2 meters per second squared. So, you know, you have to subtract 7 to 5. If it is that good, it might be 6, and then you're talking 6 to 4. So you're losing about 2/3 of your effectiveness in slowing down. So if you say, oh yeah, we'll be able to slow down 3 miles per hour per second. No, 2 miles per hour per second, because 1 mile per hour per second is being used just to hover. So that's extremely important. You got to factor in that lunar gravity. That's, again, what we call mission critical. Okay, and then the last is to perform deorbit burn using the VOR VTOL MFD. And now we're on to landing. So you want to begin adding hover thrust when you reach stopping distance as found by the total potential energy. The next thing you're going to want to do is bias the velocity vector to your pad. This will assure that you actually end up over the pad itself. When you reach a slow speed, then you want to hold it until over the base. So you'll keep decelerating, or you'll keep descending, but very slowly. When over the base, specifically the pad, continue managing your hover thrusters. And then when you're below 200 meters, gear goes down. Continue slowing yourself down to 0.2 meters per second. That's about the speed that you want to contact the lunar surface at. And last thing, when contact happens, reduce hover thrust to cutoff. And there's a autopilot which we'll be running to do the hover thrust, but that's kind of not part of what we're doing now. So we've done the mission phases, we've done the mission outline. So the next thing we're going to do is we're going to go through this list and identify what's time critical and what is mission loss capable. And this stuff is really important because I'm actually going to highlight this stuff red, yellow or red, because you don't want to get this wrong. So finding the moon map is not going to be time critical, and then you have the calculate takeoff time and azimuth are going to be no as well, and then you're going to do an orbit injection. That's going to be time critical. Your plane change is going to be time critical because it needs to be performed at a node. Well, that's not necessarily true because the vast majority of your plane change would have been done here. And once you're in orbit, your plane change, your difference in inclination really won't be changing that much. So we're going to go ahead and leave it like that. The next thing is going to be planning the TLI. Once you're in an orbit ready for your TLI, it's no longer time critical. In the case of Apollo, it would be, because you'd be dealing with consumables at that point, but we're going to assume that our consumables in the Delta Glider are much long enough to last months, which they are. So that's no problem. The next thing you're going to do is you're going to record the delta V, and you're going to calculate the burn time. Again, both of those are not time critical because if you miss a window of opportunity, you can do it at the next window of opportunity. You're just going to have to replan. But you can keep replanning as many times as you need to until you're sure you get it right. Your translunar injection burn has to happen time critical. Now, if you don't do it right, then you get free return trajectory. So you're not going to get mission loss here. So you don't have to worry about that. The next thing we're going to do is potentially a mid-course correction maneuver. Believe it or not, this is actually not time critical. We can do a mid-course correction maneuver out to about 80% of the entire trip out to the moon. Once you get about 80 to 90% out to the moon, then you begin to... It's kind of like less aiming distance. If you aim the arrow, if you're doing archery, you aim the arrow a little bit to the left. If you're far away from your target, just a teeny bit of change in aim, you're off by a mile. But if you're 5 feet from your target, as in like 90% of the way there, and you move about 3 degrees, that's an inch or two. you're not really accounting for much. So as long as you do it within 80% of your trip, you're okay. So next thing is going to be the lunar approach and the base target burn. This is also not time critical, because you can do it anywhere between the 90% region to where you're actually stopped. So in some ways, the base target burn is really a second bid course correction maneuver, which will allow you to do it without going through crazy numerical solutions. You could do numerical solutions and completely avoid this step, but it's pretty nice to not do that. The next thing is to use the vis-viva equation to calculate the orbit entry delta V. This isn't time critical because it can happen before the burn happens. The next thing is to perform your orbit entry retrograde burn. This is time critical because it needs to be done at a specific point. You can't do it at any other point. Then you get into orbit, and just like the Earth before, you're pretty stable. So identifying the base is not time critical. And then we're going to talk about doing the base transfer burn. The base transfer burn is not time critical because you can do it as many times as you need to. It's not a terminal burn, therefore using the vis-viva equation is not time critical. The using acceleration is not time critical. And then this calculation and solving is also not time critical. Tuning the VOR of the base, again, not time critical because it can occur within the window. And then you're going to calculate the distance to begin adding hover thrust. Again, not critical. And then performing the deorbit burn. That can be done as many times as you can, or as you need to. But once you start it, you have to keep going with it. So let me see what we want to do with this one. Is this deorbit burn time critical? I would say no, because we can perform it whenever we need to, really. Begin adding hover thrust when you reach the stopping distance. That's mandatory. That is going to happen. So you have to do that. Biasing velocity vector to the pad. We're going to call that time critical because you're running your hover engines at that point. When you reach a slow speed, hold it until you're over the base. Yes, that's time critical, because if you don't, then you're probably going to slam into the lunar surface where you don't want to. When you're over the base, then you want to manage your hover thrusters. Again, you're using your hover thrust at that point. Below 200 meters per second, gear down. Not really time critical because you can do it any time until you touch the surface. And to be honest, if you really do come to a rest on the surface, you're probably not going to crush anything because of the lower weight. So you'd probably be okay. Continue slowing to 0.2 meters per second. That's time critical. If you don't slow to that speed in time, you're going to be screwed. And then when contact happens, reduce thrust to cut off. No, because you're landed. So if you happen to waste engines or waste hover fuel onto the surface, I mean, you're going to take off again once you get light enough to do it. Okay, so the next thing we're going to do is go through every single one of these and determine if you can receive mission loss from it. Finding the moon on the MFD. No, that's pretty darn obvious. Calculating a takeoff time. No. Azimuth. No. Orbit injection. No. Plane change. No. Planning the TLI. No. Recording the delta V and calculating the burn time. No. MCC1. Let me see. This is mission loss. We're going to say yes. Because if you don't do an MCC1, you might find that your calculations are so good that you're heading straight for the moon. And you impact it. So that's incredibly important. Yeah, you know what? We're going to say no. Because the MCC1 is to get you specifically to the moon. What is actually important is the base target burn. Because that selects your altitude. You can do that burn to avoid the moon if you have to, but if you're off by quite a bit of distance, you're going to have some issues there. Using the vis-viva equation to calculate, you're not going to get any mission loss from calculating things. Performing the orbit entry retrograde burn. No, because you're going to get what's something called free return trajectory. If you pass the moon, you're actually going to come right back to the Earth. So you'll be okay. Okay, so now we have the base longitude and the transfer burn. As long as we do them right, there's really no capability for mission loss at that section. Again, calculations don't have mission loss. Then you have an acceleration to distance formula. Nope, that's fine. That's fine. Again, more calculations. Perform your deorbit burn. Yes, this can result in mission loss. If you don't add the hover engines in properly, then you can get mission loss by doing this. Begin adding hover thrust. Yes, again, if you don't add the hover thrust in, you can screw yourself. Biasing the velocity vector to the pad is actually not grounds for mission loss because this is a horizontal velocity vector, not going to hurt you vertically. Hover until you're over the base. No, because it doesn't necessarily matter that you come directly onto the base just so long as you're stopped. When you're over the base, you manage your hover thrusters. Yes, that's probably the biggest one. Below 200 meters per second, gear down. We're going to say probably not for forgetting to put gear down. You have to reach 0.2 meters per second, or you could get mission loss, and then recover or reduce thrust to cutoff, which is going to be no. Alright, so I'm just going to color code all of these real quick. Okay, so I've cleaned this up a little bit, and as you can see, towards the beginning we have a lot of time-critical things, but towards the end we have a lot of mission-critical things. So to be very careful when we get into the section around the moon, because it's kind of a dangerous environment. It doesn't have anything like that. So the last thing now is going to be creating the math table, and this is probably the most boring section, so I'm going to tabulate exactly what we need calculated, because a lot of times this stuff comes naturally to me. I just do it when I need to. But we want to know exactly what we're doing up ahead of time so that there's no surprises, so you don't have to be thinking as hard. So I'm going to put together a table, and then we're going to define some equations. Okay, so I threw everything together ahead of time just to make it go a little bit faster, because you can see there's a lot to cover here. So what we're going to do is we're going to enter in some bogus values that might be considered realistic in order to concept check our materials. And I'm going to work out what the actual calculations are. So let's say that we're going to be at Cape Canaveral. That's about 82 degrees west, so we'll put in negative 82 here. Let's say that the moon is, somewhere off the Strait of Gibraltar or whatever, so we'll enter negative 2 here. And so to get this calculation, this is going to be how long it takes based on a difference that you see on the map MFD. So what you got to do is you got to find the difference. So I think it's it minus u is supposed to give you the difference. And then divide by 15 degrees per hour. We should get about 4. Yeah, that's right. So this is the time to launch in hours. Again, this is an example. We're actually going to enter things in here. And to mention or to indicate to me that I'm supposed to put things in here, I'm actually going to type the word enter. That way I'll be able to tell. Okay, so the next thing we're going to do is calculate the azimuth. So let's say the moon is going to be at 7. Actually, that's a really bad. Let's say 35. And say our launch latitude is 28. So that is going to be our formula that I've put there for myself. So I've given degrees, which means you have to convert to degrees at the end. And it's going to be the arc sine of the cosine of, let me see, this number converted to radians, close that twice, divided by the cosine of this number, whoops, convert it to radians first, close it twice, and then close the arc sine, close the degrees. And so we get about 68 degrees. So let me just see, if that is 35 degrees, this is northwards, by the way. You have to do a quadrant check for this. Let's see, if this is an ascending node, then the inclination 35 degrees at 28, 68. Yeah, that's reasonable. Okay, so I'm going to consider that correct as well. Again, these are just bogus test values to make sure that it's not broken. For a main engine thrust, I think it's about 340 kilonewtons, if I remember correctly. Spacecraft mass is going to be somewhere around 19, we'll say 21,000 kilograms. Delta V for a transfer burn, this is, yeah, I should probably be a little bit more specific about this, of translunar injection. The delta V that we're going to need to do at that specific time is probably going to be about 21 meters per second. That's probably about what it's going to be. So if I just do a quick test calculation, that's my acceleration, that's my dry acceleration, that's not counting any fuel loss that will occur while I'm burning. You need calculus in order to do that, which I'm not going to get involved with just yet. So let's see, that is the acceleration, and if we divide the delta V by the acceleration, ooh, something screwed up here. Let's see, we have delta V divided by acceleration. Hang on, something's not. This is why I like to do these test calculations, so you know something goes wrong. So 3121 divided by 16, that should not be times 10 to the minus 7. Forgetting my fractions. Remember to group these up. That way they don't divide in order, because it'll be wrong. There we go. That's more realistic. So about 3-minute burn. And then this is going to be for the orbital injection around the moon. So now we want the universal gravitational constant. But real quick, let me. That's going to enter. We can get a few of these numbers before launch. We can get the main engine thrust, but we will not get the spacecraft mass until it's time to burn. This happens in real life. They call them like mass updates and mass estimates. Let's see, we want delta V. Yeah, that's an entered number. Okay. Here's another example. 6.67 times 10 to the minus 11. That's a hard fact number. We'll never have to enter that again. The next thing is the moon, which, if I remember correctly, is 1/84 the mass of the Earth. Which is 5.97 times 10 to the 24 kilograms. And stop it, Excel. I really hate that. Set this to 64. Yeah, that looks about right. 7 times 10 to the 22 for the mass of the moon. Then we need an R1 and A1. So the A1 we're not going to know until we get down to the orbit, but just for the heck of it, let's just say it's negative 15 e to the 6. And then the radius, R1 is going to be the radius at which we intercept the moon. So we probably want to do that at a really low injection. We'll say 100 kilometers just to be nice and round. So we need to add 100,000 plus 1736,000. Okay, so that's our R1. Our R1 is going to be our R2 because we're assuming that it's impulsive. And our A2, we're going to want exactly, let's see, 1/2 the distance of the major axis, which is going to be equivalent to the radius of a circular orbit, which means it's going to be equal to A2. So we can actually chug this calculation out in advance. Now, I don't have the vis-viva equation memorized, so I'm going to have to look it up. Okay, so it's going to be the square root of g times m, and those are constants. We won't have to enter them in again in the spreadsheet. Although I do want to fact check the mass of the moon, because that could be pretty far off. I'm going to clean up all of these numbers, probably, the ones that I can, before we actually fly. Okay. Times 2 over r, the first one, minus 1 over a, and close parens. 2340 looks about, yeah, that's not bad. That's actually a pretty good estimate. Wow. Okay, I do need an extra line here for DV though. And then here's a really nice thing. Because Excel is copyable, there we go. All I need to do is figure out what the V2 is, and the only numbers that I need to change are to stay consistent with this guy and that guy. So it's 2 over r minus 1 over a. Looks good. Yep, there's a circular. Now we just subtract to get our delta V. And shoot, you know what? I forgot. I need to get the burn time as well, which means we're going to need 1, 2, 3, 4. We're going to need 4 more lines here real quick. This is probably one of the biggest calculations that we're going to do. So you need 4 more lines. I think we can just about copy everything down here. Be careful when you copy and paste though. So that looks good. We'll knock off about 1,000 kilograms here. Delta V is not going to be that. It's going to be, in fact, let's get rid of that enter because it's not an entered parameter either. It's going to be equal to that. And then we get a time to burn. Looks about good. Okay, so base longitude, I don't know, 63. Just subtract 180. And if it's less than 180, add 360. Basically straightforward. I don't need to because I'm just used to it. Okay, then we're going to get a vis-viva equation calculation of velocity to kill. We actually don't need these lower parameters here because the V2 is 0. So the delta V is actually V1. So I should be able to just go right down here. 1, 2. Oh, but you know what? Before I start copying around the lunar mass, let me confirm. Okay, yeah, it's a good thing I did that because I was a few yodigrams off. 7.35 times 10 to the 22. Anyhow, let's copy these 5 rows here and drop them down here. And just check everything else out. This is 1836, yep, 100 kilometers. Oh yeah, it's going to be that number because that's the orbit that we're in. Good. So that's a self-check. the next thing we need to do is figure out distance to stop, and some of this we've done before, which means we can also do this. Now the delta V is actually known. It's going to be this, and the spacecraft mass and the engine thrust I'll put here. Let's knock off another 1,000 kilograms. And then the time to stop is going to be, again, get your acceleration. Good, 17 meters per second, looks not bad. And then take the delta V, divide by the acceleration, and you get the time to stop. So now you need the distance to stop. Now that's going to be equal to 1/2 times A, so that's going to be this divided by that times t squared. And we should get something big, like about 65 kilometers. Hang on, is that right? Let's see, 0.5 at squared. Yeah, that's right. Okay, so about 160 kilometers. The next thing we're going to do is calculate the potential energy that we experience. This m is always going to be 1 because it cancels. So ideally it would matter, but because it cancels with kinetic energy, it's not going to be a problem. G is the gravitational constant of the moon, which I can calculate real quick. It's going to be equal to G, so that's always going to be G, times the mass of the moon, which is there, divided by the radius of it squared, which is going to be, wait a minute. Let's see. If I use the upper, we want to use the lower. Yeah, we want to use the lower. We need calculus to get this answer too, because you're talking from one height to another height. So the potential energy actually changes based on its height, because gravity isn't a constant; it's a 1/r² relationship. But so we want to divide by the lower r, will give us the most conservative estimate. So that's going to be the radius of the moon, which is 1736,000. And that will give us a little bit of contingency room in case I get distracted. Oh, okay. Definitely not 10 to the 6. That's a squared. 1.63. And that's meters per second squared. You remember they say that the moon is about 1/6 in Earth gravity. So if I do an Earth gravity, which is other way around, this divided by 1 Earth gravity, 9.8. Yeah, that's just about exactly 1/6. In fact, I think that's yeah, that is insanely close to a sixth. Okay. H is going to be wherever we stop. It's going to be about 100 kilometers, so that's going to be 100,000 meters. So now we get our energy, mgh. Okay, so that's the total energy in joules of the stop situation. As we're as we've killed our orbit, we're now descending. The velocity that we're going to be picking up, remember kinetic energy is going to be, let me see which column I put it in. You see, kinetic energy is going to be 1/2 mv squared, I believe. So we need to solve for v in this case. Let me do that real quick. So it's going to be the square root of 2 times the kinetic energy, which is the potential energy when we're stopped. At that moment, we'll have 0 kinetic energy, and all of our energy will be potential within 100th or so. Divided by the mass, which is 1. Again, they cancel, so it doesn't matter. So that's going to be our velocity when we get close to the surface. So the next thing I need to do is calculate the stopping distance. So that's not the main engine thrust, that's going to be the hover engine thrust. That's a little bit weaker, so the acceleration is going to be right about 7 meters per second or so. So put your spacecraft mass in again. The G is going to be equal to the moon's G, so that carries. The hover engine thrust we're just going to estimate is 180,000 or something like that. Divide just to get acceleration, make sure that's right. 9.4, probably a bit high, so let's say 160,000. Still a little bit high, but whatever. We're going to enter that in later. Again, all of these calculations that I'm doing now, well, there's a few that are real, but most of these are just for concept check to make sure that when I run the calculator through, it's going to work. And when I refer back to the numbers, I'm going to say the value that we got in cell F96, for instance. Okay. So next we need the velocity. That's acceleration. We need the velocity to kill, which would be that. It's actually going to be slightly less than that because we need to stop before we slam into the surface. This will be the number that we will, the speed that we will hit if our hover engines refuse to light. That will be the speed that we crash into the surface with. Okay, so we're going to have a final velocity of 570 meters per second, and we need to kill it with whatever that is. But here's where you need to be extremely careful. You don't have 8.42 meters per second to slow down with because you're fighting the moon's gravity. So this is where you have to be careful. Minus the gravity of the moon. That's critical. If you don't subtract this, you will not be accounting for the gravity of the moon. You will slam into the surface. It's going to take 84 seconds to kill the speed. Please note, if that number's negative, it means one of two things. One, you did your calculation wrong, or two, gravity is stronger than your hover engines, which means your hover engines are sufficient, and that's the time that it's going to take until you die on the surface. For instance, let's say that the Earth's gravity is 9.8. We want to use them to decelerate on Earth. Uh-oh, that number's negative. If we tried to use the hover engines to decelerate on the Earth, we would die in 413 seconds if it were airless, which it's not. So, be careful. Again, let me demonstrate. If you don't subtract it, it's going to take 67 seconds to slow down. Okay, no, 84 seconds. And let's get the distance, which is going to be 1/2 times A. Watch yourself here. Subtract it. Actually, I have to be really careful here because this is going to be compounded. A times t squared relative here. Okay. So when we get down to 24 kilometers, we need to start slowing down. Again, if you don't do this, we're good. We can go down to 19. No, 24. If you wait till 19, it's too late. And that's why I consider that mission critical. The end is the most mission critical. If you wait too long, it's too late. You run your engines at full power for the next 2 minutes, or actually be a minute, the next minute, and then you crash into the surface and die, and that would be the end. So you need to be careful. Ironically enough, our very last math equation is in fact the most important. So we're going to keep entering a few things in here that need to be entered manually when we fly. G does not change. The mass of the moon does not change. Our approach orbit might change, so we're going to say to enter to be careful. And doggone it, this stupid control thing's getting in the way. Let's see. A is going to change. V1 is calculated. Let's see. R2 and A2. We might select a different orbit, so that's probably a good thing to have there. V2 and delta V are going to be calculated. That's a borrowed value. That's a calculated value. These two we're going to need to enter. Whoops, not that one, just that one, because this one's calculated. Again, these two values won't change because they're constants, and I've confirmed them now. You see 1836, that's an approach orbit distance. So that is, that's definitely a check. That's definitely a check. This is calculated. Keep going. Almost done. These are entered. Delta V should be calculated. Actually, that's inferred. Calculated. So we're okay there. This is always going to cancel, so we can ignore it. The gravity of the moon, I'm 100% sure on because I know it's 1736 and I've confirmed the mass of the moon. So we're okay. The H could change based on the orbit that we pick. Again, this is your altitude, not your distance from the center of the moon. So when we use these R1s and A1s, those are with respect to the center of the moon. This is calculated. That's calculated. That's inferred. These we'll have to enter manually. Let's see. And the reason I can't do like equals this one is because as we do our mission, we're going to become lighter. That's why I changed from 21 to 19, because it's going to decrease. Now our velocity is, you see that's borrowed from somewhere. F96. That's borrowed from this one. So we don't have to enter anything in there. That's calculated, and that's calculated. So let's see how many things we need to enter. So altogether, for our math equations, we're going to need to enter 21 unique values in order to be able to succeed in this mission. So that's what it comes down to, is those 21 values, and this math equation sheet is what I'm going to use to fly my mission. It's going to change throughout, but the structure should be the same unless we change something. Like, let's say, okay, we missed the moon, we get a free return trajectory. So with that, we've now assembled our table of math, which means the planning of this mission is now complete, and we are ready to fly to the moon. So just take this video into a different, before you watch the one going to the moon, take this into a different tab, and then take a look at this, and then I'm going to scroll down until F68 is at the top. And then take a look at this, screen snap it, whatever you need to do, and then I'm going to skip down again until 91, and there we go. That's the rest of it. So keep that off to a side screen because I'm going to be referring to it during my flight. I'm going to have it off on a separate system. So that is how we plan a simple mission. Yes, this is a simple mission. So join me the next episode where we fly this. Thank you, and bye-bye.